Good morning, everyone. I was just waiting for a few additional people to pop on. It looks like it's slowly climbing, but we'll go ahead and get started this morning. I just wanted to thank everybody for joining us on our virtual Structural Engineering Association of Pennsylvania conference this year. I am Jonathan Memel, the current president of SEAoP, and we were unfortunately, just due to the COVID situation and everything that everybody's been dealing with in 2020, you'll have to bear with us through another virtual presentation. But I think we have some very good speakers this morning and tomorrow morning for you to get some good technical webinar continuing education out of it. And unfortunately, we couldn't see each other in person this year, but hopefully next year we'll be back in person somewhere. I just wanted to thank our sponsors this year for sponsoring us on our virtual conference: AISC, Langen, Plan B Engineering, Watts Restoration, Stone Strong of Maryland, and Side Plate. Thank you for your support, and you'll see links and things on our website to their sponsorship as well. Just wanted to thank everybody for bearing with us. We probably have about 75 or 76 people that signed up to join us today and tomorrow, which is great turnout. And we're hovering around 240 overall SEAoP members right now and that have been renewing for next year, which is great to see. Just a couple of logistics on how this is going to work, very similar to some of the DVACE presentations that people have been attending, is that we're going to be sending out 10 question quizzes for each speech after the fact today and tomorrow, and that we would ask you to complete those by Friday the 20th. And then we will get the PDHs issued out to everybody over the next few weeks or so. What we're waiting for is NCSEA to finish their diamond review, and it's taking a little longer just due to staffing and everything else. So as soon as we'll communicate that out to everybody, and as we get those completed, we will get them to you. But please complete the quizzes by this Friday. Other than that, I think we can go ahead and I will introduce our first speakers of the day. We have with us this morning, we have, hold on, I gotta get to we have Amy Heilig of Dlubal Software and Florian Back of Bensonwood, and they're going to have a presentation about the rise of mass timber and the role of FEA software. Amy is the CEO of Dlubal Software, located in Philadelphia. She attended Colorado State University for her bachelor's degree in civil engineering, and then continuing her education at the University of Texas at Austin to earn her master's degree in structural engineering. After several years spent in the design industry for both bridges and industrial structures, she moved to a career at RISA, specializing in structural analysis software. A couple of years later, she accepted a position with Dlubal Software to expand their global presence and open the first USA office serving North American clients. So in addition to opening the Philadelphia office, she provides sales, tech support, and continues to aid in the development of software programs for the American and Canadian markets. She is also being, Florian Back is also presenting with Amy this morning. He's joined Bensonwood in 2017 after working in the facade industry in Germany and New York City. Prior, Florian earned his diploma engineer from the University of Applied Sciences in Rosenheim, Germany, a school that specializes in timber engineering and construction. During his program, he spent a year working at Bensonwood, learning about North American timber framing and offsite fabrication. At Bensonwood, Florian works with the sales engineering team facilitating mass timber and panelized construction projects with various architects and developers. He works on early project development as well as final engineering and preparing 3D models for production. And with that, I will turn it over to Amy and to start the rise of mass timber and the role of FEA software presentation. Thank you.
Good morning, everybody. Hopefully you're all able to see my screen. We have this PowerPoint open right now. Thank you so much for joining us this morning for this first presentation, which will be presented by Dlubal Software as well as Bensonwood. So my name is Amy Heilig, and I am the CEO of our U.S. office for Dlubal Software, and I am joined today with Florian Black, who is joining us with Bensonwood Homes, who will be presenting the second half of our presentation today. What we're going to talk about today is the rise of mass timber and the role of FEA software. So what I'd like to do here is to go ahead and I'll stop my video and we'll continue on with the rest of the presentation. So hopefully today, discussing really mass timber, kind of how we can use FEA software to aid in that. We'll be focusing mainly on cross-laminated timber. What I hope though is that even if you're not using our program RFEM, which we'll be diving into today, that you'll be able to take a lot of this information that I'm giving you and apply it with your own projects and your own FEA software. So hopefully not, too specific with RFEM. But we will be working with our general analysis program and in particular the RF-LAMINATE add-on module that's embedded within this main program for cross-laminated timber design. So I'll be going through the CLT input data as well as some of the theory behind it. And we'll be running a quick analysis and design according to the NDS 2018. Then I'll turn it over to Florian, who is an engineer at Bensonwood, to show you some real world applications of cross-laminated timber, mass timber with some example projects that they have worked on. He'll go on to talk about how they found RFEM to be a necessary and useful tool in these projects and to go through a few example RFEM models as well. So I am going to go ahead and begin within our program RFEM. So you can see that this is the main structural analysis program here, RFEM. It will provide a full analysis. So we're talking things like internal forces, deflection, support reactions. We do work with this add-on module concept to provide design of our elements, and that would include today we'll be looking at RF-LAMINATE, which provides design of cross-laminated timber. So for the sake of time, I have already modeled a two-story structure here, and you'll notice that we have several surfaces, and if I double click on one of these surfaces, the stiffness type is set to laminate, and this refers to our RF-LAMINATE add-on module, which again we'll get into in just a minute on how we can actually accurately calculate the stiffness properties of CLT panels. I've also combined this with member elements. So you'll see here glulam beams, which are dropped down below the bottom of the surfaces here for additional support. We have some glulam columns as well. So all within the same project here. I've also applied loads to this structure. So these are just general surface loads. You can see here, maybe if I turn this to wireframe, it's a little bit easier. We have a dead load applied to the first level and the roof level here, a live load, simple snow load, again, just an application at that roof level. And then we have a lateral wind load. So I went ahead and combined all these load cases into load combinations according to the ASCE 7. So when we display these together, you'll see these gravity loads in addition to lateral loads kind of acting on the structure altogether. But the initial, before we run this initial calculation, what's required here is to define the correct stiffness types for our cross-laminated timber. And for this, we would utilize this add-on module RF-LAMINATE. And I can access RF-LAMINATE within my project navigator over on the left. And when I say add-on module, it's really nothing more than just this dialog box that pops up within our main program. So before I give you a quick tour here, let us jump back to the PowerPoint to kind of see what's happening behind the scenes with this add-on module, how it's working with RFEM, the main program. So we know with cross-laminated timber that this is going to be individual layers oriented 90 degrees. And each individual layer has its own stiffness properties. So we're talking modulus of elasticity, shear modulus. So in turn, these individual layers have their own stiffness matrix as well. So this is what eventually we're going to be defining within RF laminate, are these individual layers. Well, what we do with these individual layers is to create this overall panel. And what's required for this panel that we might use for a wall element or floor element is to generate the overall stiffness matrix. We call this the global stiffness matrix here of this panel. So RF laminate will automatically do this within the background with what's called the laminate theory. So you might see here a sample calculation for the D11 entry of that stiffness matrix. Well, we take this global stiffness matrix and we're going to export it from the add-on module back into RFEM. So we're talking about that structure we were just viewing. And we can go ahead and run the analysis. So this includes the dead load, live load, wind, snow load. And after we run this analysis, we're going to get internal forces for each one of these CLT panels. Well, we take these internal forces from RFEM and we're going to actually bring them back into the add-on module. And we distribute these stresses to each individual layer. So here might be another sample calculation here for separating out those stresses. Now, if we take a cross-section of our CLT panel, we might see the stress distribution look something similar to this. Well, from here, we separate out all of these stresses into tension, compression, bending, and shear components. And these stresses from the analysis are ultimately what we're comparing with our design stresses or our limiting stresses based on the material as well as based on the NDS code. And from this, we finally get a design ratio for our CLT panel. So that's kind of what's going on in the background here. So jumping back to RFEM, again, just to give a quick tour of what this add-on module requires and the input, you can see that I can choose the surfaces that I'd like for design. Now, currently, I've only selected the roof panels here as well as 3 wall panels. We could design all at once if we wanted to. Over on the right-hand side, we're going to choose our design standard. So you can see the NDS. We know recently the NDS has added CLT design with the 2015 standard. We also have the 2018 standard. We have the Canadian standards because, again, that was recently implemented there. And then, of course, the Euro code. So for the ultimate limit seat design, we would likely move our LRFD load combinations over here to the right, and that's just simply because I'm choosing the design method according to the LRFD. Notice the ASD is also available here. We also can check serviceability for these panels. So we're talking deflection checks, and I'll show you a little bit later on where we can set that limiting deflection ratio. Now for this simple example today, I'm not doing deflection checks, but we'd probably move these unfactored ASD load combinations over here to the right-hand side. So it's really as easy as moving down these tables from top to bottom. So we'll take a look at this next table, material characteristics, and this relates back to the PowerPoint model of where we're defining these individual layers for our CLT panel. So for the first layer here, we can access our material database, and we use our filters over on the left to filter to timber. We might choose North America. We could choose the NDS 2018, and here's about every single timber material available within the standard. And of course, all of the relevant material properties. You can use these search functions if you need to as well. But once you've determined what the material is for that first layer, we would select it. You would want to choose input in here the thickness, and notice in this third column is the orthotropic direction. So 0 degrees, 90 degrees, 0 degrees, and so on. That's the definition here of CLT, orienting those 90 degrees from each other. And then we're going to get the modulus of elasticity and the shear modulus automatically brought in from that material property or material database. So we'd continue to do so for our additional layers, and this might be for a custom layup, a custom type CLT composition. We could save these layers so that we can always use them in a future project for mass timber here within RFEM. The other option is to import the layers from the library. So within this option, you can see a drop-down box here of some various manufacturers. So when we're talking CLT from the North American market, some names that might sound familiar: Nordic Structures, Smart Lam, you can see Structure Lam, and then we just have the general PRG 320. So for example purposes, we might move forward with PRG 320 CLT according to the US. So once we select our manufacturer, we would choose our grade from the drop-down. We would choose our thickness, which is going to influence the number of layers for our CLT panel. But notice that the layers are automatically brought in, the thicknesses, the directions. And when we import that in, this entire field or this table will be filled out for us based on the manufacturer's products. So just another option if you do see your manufacturer in there. Otherwise, you can create those custom layups and save them to your library. Now, again, relating back to the PowerPoint, each one of these individual layers has its own stiffness matrix. So we can actually view the individual stiffness matrix here for that single layer. Well, the program takes it a step further, of course, and it calculates this global stiffness matrix for our panel. So this might be something that if you're not utilizing a program where you can individually define these layers, you're going to need to put in the global stiffness matrix into your relevant FEA program. So this might be something that perhaps you get from the manufacturer, but ultimately this is the information we need to export back out to RFEM. So you can see here that I named this composition floors, and I've applied it here to all of my surfaces that are my floor elements. And we can create different compositions for the roof versus the first floor. That's all possible. Exact same concept for my second composition here, my wall elements. And this time I also just have 3 layers for my wall elements. Perhaps we have 5. You can see that I've applied these to all of my wall elements back in the RFEM model. So before we move forward here, there are some details within these compositions that's really important for analysis, and we can visit those under the detail settings here. So you'll notice we have several options that we can check on and off, as well as stiffness reduction factors. So in order to discuss this a little bit further, I'm going to jump back to this PowerPoint. So here's just a simple screenshot of those first checkbox options, and you can see here the consider coupling is the first one, and this typically is going to be turned on by default. What this means is that we have glue at the top and bottom of each layer, so we have kind of a coupling behavior between each one of the layers. Now, when we're looking with this option checked on, this would be relevant to our snapshot over here on the left with coupling. So this is a cross section of our CLT, 5 layers in this example. Well, we might see this stress distribution for something like shear stress looking similar to what's shown on the right, normal stress on the left, but notice that there's a relationship here between all 5 of the layers. When we turn this option off, or assuming we don't have glue or bonding between the top and bottom of these layers, and the stress distribution is really going to be individual for each one of these layers. Notice we don't have that same relationship between all 5 layers now. It's really independent. So typically, again, you probably will have this checked in most situations. The second option, the cross-laminated timber without glue at the narrow sides, this is really specific to the manufacturer that you're using. And this all relates to edge bonding. And we can see this picture over here on the right, a very exaggerated picture of a cross-section of CLT. We know that for each individual layer, the boards are essentially adjacent to each other within one of these layers, kind of similar to what's shown here. Now, again, very exaggerated picture, but what we mean without glue at the narrow sides, we do not have glue in these gaps here. So the boards are not bonded to each other in a single layer. So when we have this option checked on, we're automatically going to assume your modulus of elasticity in the y direction of the surface is equal to 0. So we really don't have much stiffness in that orientation of the panel. Now, it's highly recommended that you also reduce the stiffness. We would apply a stiffness reduction factor, K33 and K88, which in turn relate to the stiffness matrix entries D33 and D88. So K33 is related to torsional stiffness and K88 is related to in-plane membrane stiffness. Now, I want to discuss this a little bit further on the next slide. So the NDS, as well as the Canadian standard, CSA standard, really do not address glue not being applied at the narrow edges or edge bonding at all. It really goes on to say nothing about this. So what we would refer to here is actually the Eurocode, the EC5, and in particular the Austrian Annex, which lays out very clearly what to do when we do not have edge bonding and how to calculate K33 and K88, those reduction factors. So it does require a few variables for the equations, and we can see the initial variables are given to us here, the total thickness of the CLT panel, the number of layers. So in our case today, we have 3 layers. The board width, today's example, 4 inches. This is information we get from the manufacturer. The board height, 1.37 inches. So taking a look at the next slide, we also have some additional variables that are given directly in the EC5 Austrian Annex. Depending on the number of layers, 3, 5, or 7, you'll see these variables here, PD, QD, and so on. Well, these are also needed for the K33, K88 equations. And those equations are listed here. Again, directly from the standard, it's laid out quite clearly how we need to reduce the stiffness when we don't have that edge bonding. So we take all these variables from the previous slide and from our table here, and we're ultimately calculating K33 as 0.435 in our example today. Well, this is the information we apply directly in the program under those composition details. Same concept for K88. We're going to apply those directly here. Now, for some of the manufacturers, these values are included if they don't have edge bonding. For others, maybe we weren't able to get this information. So always just something to double check for your particular project, your manufacturer, and which CLT panels you're using. And again, not specific to RFEM, but this would be a stiffness reduction you'd want to apply with your own analysis tools. The final consideration here for these check boxes up at the top is shear failure and glued contact surface. And this actually all relates to torsion. And we're really mostly concerned with torsion when we're talking about CLT wall elements loaded in plane. We're probably not so concerned with torsion when we're talking about floor elements, for example. Now, this really is also only a concern when we don't have glue at the narrow sides again. So this first checkbox must be checked. That will make this third checkbox available here that we can go ahead and take a look at torsion considerations. Just a small tip, it's really important to set the FE mesh back in RFEM. So our FE mesh settings for the length approximately equal to the board width. So in our case, that would be 4 inches, just for the most accurate analysis. Now, once again, the NDS standard, the CSA standard don't address torsion whatsoever. So we refer back to the Eurocode 5, the 2010 version. I think we're all kind of in agreement that the European standards have been doing cross-laminated timber much longer than what we've seen here in North America. So it's pretty safe to say we can refer back to these standards for considerations such as torsion. And once again, complete interaction equations given quite clearly directly within the standard, and we can see those interaction equations in the lower left corner here. And this includes 3 different terms. The first term can be shown over here on the right hand side, the second term lower right hand side, and then the third term would be those internal forces and stresses directly from the RFEM analysis to ultimately give us our design ratio for torsion for our wall elements. Now, over on the right-hand side, you'll see that we have all of these different stresses available to us within RF-LAMINATE. And it's pretty overwhelming. So what we've tried to do is to just only check on the check boxes that are relevant for CLT design. Now, this includes the top and bottom layers as well as the middle layers, and torsion is actually not one of them that we have checked on by default. So I'll show you in just a minute how we can go ahead and turn those on in order to take that into consideration for our results that are being shown. So we'll go back to RF-LAMINATE. If you remember way back when, we still have this dialog box open, and we're currently looking at my wall elements, and we are considering coupling. We don't have glue at the narrow sides. We are concerned with torsion, so we want to go ahead and put in here our plank width or our board width equal to 4 inches. And just like I showed in the PowerPoint, I calculated K33 and K88, which I'm inputting in here as well. So for my floor elements, if we jump back to those, same exact concept, but I'm not concerned with torsion here. So we can leave that option checked off, but we're still applying that stiffness reduction factor K33, K88. So once we have input in all this information here for those material characteristics, we can just jump down to our next table, material strengths. Really not much to do here. Everything is brought in from that material library. It's just showing us the strengths for bending, tension, compression, and shear. So this information based on the material itself, the material properties, in addition to the NDS factors, is what's going to give us our limiting stress values. And so when we're talking the NDS factors, we might be looking at the load duration factor, which we can see is set within this next table. So dead live snow wind, we would set the load duration factor here. In-service conditions, is your CLT panel dry? Is it wet? What is the temperature it's sustaining? And all of these factors are actually found under the standard tab. So we can see here the relevant factors that are going to be applied for the design purposes. You'll also notice the second tab here, serviceability limits. That's what I was talking about. We also can check deflections where we set this limiting deflection ratio directly within the program. We're not checking serviceability today, so this isn't applied, but just to let you know it is available. So before we're ready to run our calculation, remember I wanted to turn on the torsion checks, so we can do that under the detail settings. And once again, here's this long list of all these different stresses that we can compare and give design ratios. Way too overwhelming. So we have just the default settings here, which likely is going to be most relevant for your CLT design. But here in kind of the lower portion is where we can activate the torsion checks as well. So we're almost ready to run that calculation, but before we do so, let me jump back to the RFEM program. And again, this is just our main structure, and you'll notice that we have all of these symbols kind of shown here, these blue symbols shown everywhere. So we might be wondering, well, what are these used for and why are they relevant? And again, incredibly important for the true properties here of our CLT structure. So let's begin with a couple of adjacent panels, and I'll highlight these and we'll take a look at just the visibility by these selected objects. So two CLT panels side by side, and I'd say in most FEA programs when we're modeling two surfaces side by side like this, the program is going to assume that we have a fully rigid connection between these two panels. And we all know with CLT design that that's not the case. Rather, we're going to be utilizing some type of screw connection maybe, where we kind of have this partially fixed connection, but definitely not a fully rigid connection. So that's why we would utilize in the program what's called a line hinge. So when I double click on this line hinge, you'll notice I have the ability to fully release the moment between the two panels. So that's probably one consideration we want to take. We also have the ability here along the joint length to set some type of spring constant, and this might be for kind of the slip of those screws between the two panels. For my example today, I set this to 50 kips per square foot, but this would all be relevant to the type of CLT connection that you're using for your projects. The other 2 degrees of freedom here, translation in the Y and Z direction, are left at fully fixed. So this is definitely something that you need to apply, and this is why you're seeing, when I cancel out of this visibility mode, these line hinge symbols kind of shown everywhere throughout the panel connections. The other symbol that we're looking at here are these long blue lines. And for this, let me go ahead and create a user-defined visibility here, just so that this is a little bit more clear. Well, similar to our adjacent panels, we have these beams, drop down below the CLT panels just for additional support here, these downspan glulam beams. Well, very similar to what we're seeing with the CLT panel connection when they're adjacent to each other, this is going to assume a fully rigid connection between this beam as well as the CLT panel. Once again, we know that's not the case because of these screw type connections. So we need to adjust this fully rigid connection here. And we do so with what's called a line release. So when I double click on this line release, it's actually very similar to a line hinge. It's just a little bit more applicable to beam to panel connections. So with this, we can define the line release type by releasing the moment. Once again, we can see that here. And then we're also going to apply that stiffness slip to the joint along the local x-axis of the line here. So 50 kibs per square foot. The other two, we kind of leave these as fully fixed. Now, another advantage of a line release over a line hinge is the ability to define nonlinearity. So you're going to see here friction, partial activity, and so on. Where this might be relevant is in the vertical direction. Maybe we have a scenario where we would like full force transfer when we have the CLT panel bearing down on the member, but in the event of uplift, we want that to be completely released. So that's all possible with these nonlinear applications here. So that's kind of why we have these definitions here, these line releases everywhere where we have a beam kind of connecting to the panel above it. Now, the final application here, which we'll notice, is these rectangular blue squares. Well, these are going to be used for singularities. And where might we see a singularity? Well, we convert this to a wireframe view, and we know from general FEA programs, and this is true not just for RFM, but for all programs, that members are represented here by single line elements at their centroid. So this column is just a single line element, and it's framing into these 2D surfaces at this single tiny FE mesh point here. So you can imagine the amount of stress or internal forces and this huge spike that we're going to see at this single FE mesh point, just simply because we don't have great load distribution. So again, this is not unique necessarily to RFM, but singularities happen in all FEA programs. So you're going to have to find some approach or some way to really level out those singularities. Well, in RFM, we can apply what's called an average region at these locations. So an average region is exactly what it sounds like. It's going to average out the forces over a specified dimension. So I've set here 2 feet by 2 feet. I'm averaging out the forces in all 4 directions, and we can kind of smooth out those high peak forces, internal forces and stresses that we know aren't going to exist in a real life application, but kind of they're not really avoidable when we're talking FEA design. So that would be another application here of why we kind of have these average regions shown within the structure. So canceling out this visibility mode, that will go ahead and explain why we're seeing all of these blue symbols kind of everywhere. Now, these average regions can be taken into consideration within the add-on module RF-LAMINATE as well. So once we've applied all these line hinges, line releases, average regions, if they're necessary, we're finally ready to run the calculation. So we'd hit calculation here within our add-on module, and we're presented here with our results in table format. So we can view the max stress ratio by surface, for example. If I kind of pull this down here, you'll notice that as I'm scrolling down through this table, everything's synced up in the background to highlight the surface that I'm looking at. Maybe a little bit difficult for you guys to see, but there is a red arrow here pointing exactly to where my controlling stress point is for that particular check. So that's a nice feature if we're just kind of trying to see relative to the table, to the structure in the background, where exactly we're at. But taking a look at the actual data that's presented in this table, well, this is where we're going to see each individual surface in each one of these categories here. And we're going to see the bending stresses. We're going to see tension compression stresses. We're going to see combined bending tension compression as well as shear. This does include rolling shear checks as well. And then remember those torsion checks that we've also activated. So within column J here, we're seeing the existing stresses. So this is purely from the analysis, which if we remember way back when to the PowerPoint, we're bringing in these stresses and we're separating them out to each layer into bending, tension, compression, and so on. Well, column K here is going to be the limiting stresses. So this is just based on the material as well as the NDS standard and those factors being applied. And ultimately in column L, this is where we're getting our design ratio. So we can go ahead and filter this information. We can export at the click of a button to Microsoft Excel if we need to sort a little bit further. But ultimately, we're seeing a max ratio here of 0.94 for our example today. We have our green smiley face because it's less than 1.0. As we also know from the PowerPoint, I talked about the stress distribution for each of the layers. We can see those stress distribution diagrams shown here as we kind of click through all of these different applications here for each one of the surfaces. So in addition to all of this information being shown in table format, of course, we can always jump to the graphics view here. And this is the results from RF-LAMINATE. We can see it selected here within our drop-down box. We're just viewing them graphically back in RFEM. So we can scroll to the different load combinations here if we're interested in those results. We can take a look at our wall elements, but we can also switch to our floor elements. And with these additional options here, we can also take a look for our floor elements. We might be interested in the bending stresses, for example. We can also take a look at the tension compression forces. Shear, of course, is something that we're also considering. Jumping back to our wall elements, you know, we're probably most interested in shear. Things like tension and compression are also shown available to us. And of course, we can view the design ratios in color formats as well. So can print off these pictures into our printout report and you know, take a look at the results in just something other than table format with numbers. So hopefully this was, you know, was just a quick introduction to CLT design. And like I said, you know, some of this information that we're taking away from this first part of this presentation into your own programs or your own design methods is consideration of that global stiffness matrix. You know, do we need to reduce some of the entries such as D33 and D88 if we don't have glue at the narrow sides? And then also back in the RFEM model, things like line hinges to make sure we don't have a fully rigid application between adjacent surfaces, line releases, and so on. So with that said, I will go ahead and turn it over to Florian for the second part of today's presentation.
Thanks, Amy. This is Jonathan. Real quick, just as an announcement to everybody. If you have questions throughout the presentation, I forgot to mention this beforehand, go ahead and populate it into that Q&A, and I will monitor that at the end of the presentation. Thanks.
Thank you. This is Florian. I work for Bensonwood, and I'm just gonna start the screen share. You guys should be able to see it now. So yeah, I work for Bensonwood. We have like 3 main brands. One is Unity, which are a more affordable version of a prefab home. The other one is Open Home, which is a collaboration with Kieran Timberlake and Lake Flado. And then the third option is Tectonics, where we offer our building components, which are wall panels and timbers, to any construction company or engineering company that would like to use them. A little bit of history. The company was founded in the 1970s by Ted Benson. He was back then. It was mainly focused on timber framing, traditional timber framing. It it was initially done a little bit on site, but Ted very soon realized that it could be way more efficient to work off-site and to do as much work as possible in the shop in a controlled environment, and that was one of the main focuses of the company right from the beginning, to constantly push, try to do as much work as possible in the shop and then ship it on site, and then just install it on site. Throughout the 1980s, the company used more and more machinery and more CAD design, and just trying to get more and more efficient. In the 1990s, they started to offer panels as well, insulated wall panels, floor panels, roof panels. Initially, the installation was done with spray foam. And again, all that was done in the shop. We would build panels in the shop, often with the windows installed, insulated, close up the panel, and then ship it on site and just install it on site. In the 1990s, they also used the first CNC machine. And then in the 2010s, production got more and more automated and more computerized. And you can see on the pictures on the right, that's what it looks like today. What you see on the top is called a robot drive. It can cut timbers up to 12 inches in width, 48 inches in depth, and the length is, it's kind of debatable. I mean, we actually created a little door in the wall so we can feed from the outside if we really want to feed long timbers through there, but the efficiency kind of goes down with like anything longer than 40 feet. It's what they call a 6-axis machine. It has tons of different machine heads and saws, and can cut all kinds of joinery. And then the picture, the lower picture is our panel shop that we opened in 2017. Again, it's highly automated. The panels get built, and they are on some. They like get transported through the shop on some kind of car, and they just move along. There's the nailing is automated, and then on the left you can see where the cellulose insulation gets filled, and then a little later in the shop it get put upright, windows get installed, and yeah, that's what it looks like today. All right, enough about Bensonwood. This is the first project that I wanted to show. This is called the Conversation Plinth. It's more of an art project than it is a building. It is open to it was, I should say, open to the public. You were able to walk on there, and you could stand on top. But it was just a temporary construction. It is CLT, and it's not really protected. It's outside, and so it was just a temporary installation. But of course, it had to be fully calculated because people were using it. The project is made out of hardwood CLT, which is pretty unusual. But there was an initiative in Indiana to promote the use of hardwood, locally grown hardwood, and so they came up with this installation and came up with a custom layup of a hardwood CLT. And all this was done in RFM. You can see the model on the right. I don't have the model available, but I have this photo of the model. And so what's interesting about this is that that it's just point supported. So the floor of these individual levels, they are supported by steel columns, and I mean, you unfortunately can't see in those pictures, but there are no headers or anything underneath. It's just point supported CLT, and that is one of the great things about CLT, that you can it has biaxial bending capacity, and so it can just be point supported. I'm not sure if there really is a way to calculate something like that by hand. There probably is, but it would be really difficult. So software like RFEM comes in really handy because it does all the checks in the background, and it makes the whole process a lot easier. There's a lot of applications where CLT is just used as like a plank, basically, with a simple span. And that is relatively easy to do by hand, but if you want to use the full capacity of the material, then you will sooner or later run into situations where you want to use the minor bending capacity or biaxial bending, and then there's really no way around FE software. All right, I think that's it about that project. The next project I would like to talk about is this Haus Gables in Atlanta. The architect on this is Jennifer Bonner. Again, she, when this was designed, had in mind to really celebrate the use of CLT, as you can imagine. So everything in that building is basically CLT. So the walls, the roof panels, the floors, partition walls, even the guardrail for that balcony, she was really trying to use it as much as possible, and kind of test out what's possible to do with this, well, somewhat new material, I guess. There are no beams in this roof structure or in the floors. It's all CLT floors that support themselves, and then there's some walls, but especially in the roof, yeah, you can see that how this could be utilized. The only steel beams are in here. You can see those too, because the span was a little too long, and the wind deflection didn't quite check out. There's no floor behind this. And yeah, we didn't want to increase the wall thickness just because of that one situation. So we have 2 steel beams in there, but everything else is just CLT panels. This again was this was done before we had our RFEM, the program, in-house. So we had someone else use RFEM and do the calculations, and we just provided technical support in this case. But this is the model. That's the RFEM model. You can see there's all these line hinges that Amy was talking about. They are very important to get those right. They obviously depend on the size of the screws and the spacing, and I'll talk about this a little later. Here's some pictures from the inside. This is the roof. You can kind of see the CLT panels there. They're about 8 feet wide. In this case, the architect really wanted to get the CLT panels from Europe. So they came from Austria, from a company called KLH. They're one of the pioneers within the CLT world. They might have been the first, if not definitely one of the first, that started producing CLT. And for some weird reason, it was competitive to ship those panels all the way over from Europe, and yeah, that's how it came out. Yeah, you can see here again on the inside, all of the CLT is going to be visible. So this picture here is before any finishes were applied, and this is after the finishes are applied. So you can see there's not much of a difference. There's definitely a finish on the outside, the insulation and a stucco finishes on the outside. Not sure if I have a picture of that. No, unfortunately not. But it's definitely celebrated on the inside to show what's possible with CLT. This is a project on Long Island, and it was a collaboration with Lake Flato, the architects, and what we were trying to do here is, maybe I'll skip a little bit ahead. So this centerpiece from here to about there, there's no floor inside, and they didn't want any tie rods in there. Moment frames didn't seem feasible, and obviously, like, spanning a ridge that long wasn't really an option. They just wanted to have one great open space. It's about 50 feet long, and so what we came up with is using the roof, using a CLT panel that you can't see in this picture, in the roof, and stitching them all together and creating this as like a deep beam diaphragm. So you wouldn't need any tie rods or moment frames, or there's just these braced frames at the end to take all the wind load and all the outward thrust that is otherwise not, yeah, that needs to get resolved from here to the end. This is the catwalk model that we used, and then this is the RFEM model. And for this project, I'm actually gonna switch over here. So that is the actual model. I did also work on that, so I can talk a little bit more about this one. I'm going to open one of those panels. As Amy explained earlier, that we're using the laminate module here, so the whole built-up is defined in the other module. I'm opening this to show how those hinges work. So there's, on all four sides of this panel, there's hinges defined, and then the rotational release is always set to 0 because obviously there's no moment connection there. And then we went so far to define all 3 of the other connections with springs. This is a little bit of a process, but it's very important to get that right because it has a lot of influence on the stiffness of the whole building and deflections. The way we did it here is we would build the model and have all this set to infinite stiffness, and then just run the calculations, look at the forces that are there, and then come up with a screw size and screw spacing that would work. And then we put this into an Excel sheet, and then look at the stiffness that would provide, and then put that stiffness into those boxes, run the calculations again, see if the deflections and the forces check out, and do this for a couple of iterations till we're happy, till we don't feel like there's a ton of screws, even though there are a ton of screws, and the deflections are still acceptable. That kind of process needs to get done for a lot of those connections. This one here is different because we're collecting a lot of the load along this one where the braced frame is. I'm going to show some results. What I found most interesting is the deflection of this. That was our main concern. You can see it's on Long Island on a bluff, so the wind loads were pretty significant. Unfortunately, there's no results for this one. Yeah, so you can see the results here. We analyzed the whole building as in one model, which we usually don't do, but in this case, there was just no way around it. And you can see the drift that we're expecting here is about 3/8 of an inch, and that's also what we wanted to limit it to. I'm going to jump real quick into the module. Amy was talking about that before. I'm just going to go over this from like a real-world example that is standing in Long Island as we speak. So what we used is a Nordic Nordic CLT in this case. It's from Canada, Quebec, Canada. They use black spruce, very small dimensions often. They have very small trees, but they glue it all up into big beams and CLT panels. In this case, we weren't so much interested in the actual span capacity. There were rafters in the roof, as you saw in that one picture. So the span was really not the main focus. It was more the focus on building this into a nice diaphragm. So a simple 3-ply was good enough. It's very easy to import this. Nordic CLT is built into the program, so you just pick your manufacturer, and then the type is US. They only have one type really, and then they offer different thicknesses. This is not what we used. That's a 5-ply. So let me check that. Actually, this is the one that we used, the 4 1/8. And then if you click OK, it just imports it. I'm not going to do that because it will delete the results if I do. Yeah, so that's how that module works. I don't have results in here right now to show. I'm going to go back to the presentation. That's what it looked like on site. You can see the CLT here. Those are the actual CLT panels. They were on the outside. Installation was on the inside. Yeah, and that's the great open space that they were looking for, and that we were able to achieve without the use of too much steel, and definitely without moment frames. Someone might ask, why would you need CLT for that? That's a good question. It's not necessary. It could have been done with sheathing as well, but I personally wouldn't have felt comfortable doing something like that with just I don't know, 1/2-inch OSB sheathing. The forces were pretty high, and I don't think that would have been a good solution. This is another project. We never got to build this one. Unfortunately, it was just a concept. It's in Washington D.C. and the architect was looking for again some kind of a folded roof structure that was self-supporting. This is the CLT, the RFEM model. We decided that CLT would be the easiest way to do this. Again, due to the biaxial bending capacity and the high shear capacity. So we were able, sorry, I should mention, so there's support all the way around, And then there's these two interior supports that we couldn't do without. So there's a wall here, and then there's two more walls over here that hold up the roof. But everything else, there's no more, there's no other supports in there. And we were able to prove that it's possible to do this with CLT panels. It's essential to break up the model into actual panels, like the actual panel width, so that you can model the edge correctly from one panel to the other. Since this was only a concept, we did not go so far and define the spring constants for the connections there, but definitely create a moment hinge at the panel seams. Again, there's no beams in here. It's just supported by the exterior walls and those two interior walls. And I'm not sure how to do this without an FE software. It's maybe it's possible, but it's definitely way easier to do something like that with a program like RFEM, where everything is predefined. This is the dead load deflection. The dead load and snow deflection is 1/2 inch, and then so you would expect you get these load spikes here, and there certainly would be more analysis necessary to look into those locations, and I'm very happy to hear that there is an average region available now. I did not know about this, but that is definitely something that will help a great deal resolving situations like that. Here's another project where we used a lot of mass timber. This is the Common Ground High School in New Haven, Connecticut. It was a collaboration with Gray Ogansky. Again, the timbers came from Nordic. That is all the glue lamps and the CLT that was used. In this case, we also provided the insulated wall panels. Some of the highlights of the project are these massive trusses. You can see a person right up there. They span. They provide a clear span for a gymnasium. All these timbers are from Nordic. The trusses were built in our shop, and then they were shipped to Connecticut, which is about 3-hour, 2.5-hour drive away. On an oversized truck. Again, the focus of Bensonwood to try to prefabricate as much in the shop as possible. Those wall panels you can see, they were all built in our panel shop and shipped on site with a truck. This is one of the CLT applications. So what you're looking at here, this is a CLT panel, and then those are I-joists. It's a very long span, and neither the I-joist nor the CLT on it by its own could span that far, but combined, it was possible to span that distance. You can see there's a lot of screws in here to create a shear connection. Unfortunately, at the time, we did not have RFEM yet. And so there was a lot of hand calculations and probably some extra screws to be on the safe side. With a software like RFEM, this could be done much easier, and deflection results are way more accurate doing this with an FE software. This is the model that we used at the time. That's a visual analysis. We did again use some diaphragm action here to hold up the roof. It was not quite as extensive as on the North Fork project, and it was in this case it was only sheathing. The sheathing was OSB like 5/8 or 7/8, and it would have been better to have a program like RFEM to really get the full potential out of the mass timber. That's what it looks like inside. That is one of the trusses on the right, and then there's another truss over here. There's a floor above. And one other thing I wanted to mention about this project is that the elevator shaft was built out of CLT as well, which has a couple of advantages to use CLT there. It's not always possible to get the fire rating out of the CLT as it's needed for an elevator shaft. I think in this case as well, gyp cladding was necessary to get to code. But we still think that it is a good investment to use CLT for something like that. One reason being is material consistency. There's a lot less coordination necessary to if there's just fewer trades on the job site, and whoever builds the rest of the structure can provide the elevator shaft as well. It's much faster installation time. And of course, there is the advantage of the carbon sequestration. As we all know, CMU, or really any other building material, produces carbon, whereas wood stores carbon. And that's my part of the presentation, and I'm ready for, or we both are ready for questions.